I begin with some thank yous. Hello, everyone. Welcome. My name's Chris. So I'd like to thank the organisers, Andrew and Patrick, for organising this great seminar series. Thank you for the invitation to speak at it. This series has gone on now for several seasons, and it's a privilege to be here. Thank you to the audience. Thank you to those who are here for attending. And I'm going to talk about the titles on the slide, thanks to the funder, the Royal Society of Edinburgh, who supported this work. Okay, so I'm going to discuss recent work on passivity theorems for input to state stability of forced Lur'e inclusions and equations and consequent entrainment-type properties. There are a lot of words in that title, and over the process of my talk, I will try and explain each of those terms. I'm sure many of them will be known to this audience. So in particular, I'll tell you about Lur'e systems, the passivity theorem, incremental ISS, and then what I mean by entrainment. In talks, I prefer to try and focus on ideas rather than technical details. I think ideas work better in talks, but I realize that means I might be a bit imprecise or sloppy at times. I will indeed try and provide some background and motivation, and I've shared the slides with the organisers, so I'm very happy for them to be shared. So working backwards from those key ideas that I had, entrainment, roughly speaking, means the response of a system to an almost periodic or periodic input or disturbance, and then the existence and stability or attractivity properties of any resulting almost periodic state. And one way to approach the entrainment property is via incremental ISS, and this has been known for some time, right? I cite a work of Angeli there. Now, I'm going to work on Lur'e systems or Lur'e inclusions, or rather work on Lur'e systems, and I want results which are in the spirit of absolute stability theory. So what I mean by that is that they do not depend explicitly on the nonlinear term. So we need to ensure some uniformity with respect to that nonlinear term, and one way to do that is to work first with differential inclusions, like Lur'e inclusions. And that leads to the first result, which I hope is of independent interest, but that was one of the motivations for doing it. So each of these ideas I will discuss during the presentation. Okay, Andrew already gave a nice biography about me. Thank you very much. So I don't dwell on this too much, other than just noting that control theory is broadly applicable. It's one of the nice ideas of working in it, because ultimately, if you view systems theory as the study of dynamical systems which interact with their wider environment, well, that's almost everything. So it crops up in kind of many places. So the bulk of this presentation will be on the theoretical work, which is in the title. However, there is some sort of possible distant application in the background on wave energy conversion, and I talk about that first. So a bit of background here. Modern research on wave energy conversion arose in the 1970s as a response to the oil crisis. And why are people studying it? The sort of need now is kind of clear in that it's to tackle the climate crisis, right, and reduce our CO2 emissions. And in places like the UK, to try and improve national energy security, so reduce your reliance on foreign oil and gas imports and so on. Wave energy, if anything, is at the pre-commercial stage. It's not yet commercially deployed. And why is that? Well, it's the technical challenge of successfully extracting energy from the sea, which has led to the energy being too expensive. However, the wave energy community, people working in it, strongly believe in its potential, right? And there's lots of work and evidence to highlight its potential benefits, right? So I show you two screen grabs from the IEA on one of their roadmap kind of glossy documents. And I appreciate it may be a little bit small, but they highlight the potential benefits in terms of energy, jobs created, boost to the economy, and reduction in carbon emissions. The UK is an island. It's got a favourable geography for renewable wave energy. And so in 2020, the UK government produced the following report, which highlights that between about 3 and 20% of UK electrical energy needs could be met by wave and tidal energy. So whilst that's not everything, it's not nothing. It could contribute as sort of part of a portfolio of renewable energy. So just to speak a bit about wave energy, I've got this sort of little toy diagram which highlights you're essentially trying to turn the motion of the ocean into useful electrical energy. So you're trying to convert one motion into electrical energy. So it comprises the kind of combination of fluid systems, describing the sea or ocean, mechanical systems, and electrical systems. And as I'm sure you're aware, that solar and wind are established, proven renewable energy technologies, and wave is not, and wave is currently just too expensive. And it has a lot of moving parts, both kind of literally and figuratively. On the one hand, that's good because it means lots of people can contribute, including very sort of theoretical people. But actually, no single person is going to solve this. It's not just a control problem. So I list here some of the areas that are sort of still being worked on and still where challenges still arise. This is an opportunity to include pictures as much as anything. I comment that for theoretical researchers, it's really important to work in a sort of systems agnostic framework, as there's still no apparent emergence or convergence in technology. So which technology is going to win? So okay, this report is a little bit out of date now, but many technologies have been in development. So I show three different images, and the point is these are all different types of wave energy converter. They're all trying to make electrical energy, but they do it in slightly different ways. So sort of stepping back and trying to see the themes that emerge, if you look at the wave energy or wave energy control literature, frequency domain methods seem very prevalent. Yeah, there's a kind of classical control engineering set of techniques, but obviously they're predicated on linear systems. Linear systems are themselves predicated on small deviations from a set point, right, where assumptions of linearity are valid. But in wave energy, you're essentially trying to amplify motion. You're trying to create a resonant phenomena of a device with the C to create electrical energy. That violates your assumption of linearity. Okay, you've got mechanical and electrical subsystems. Ideal models of these are linear. You might then have some nonlinear terms, and that will give rise to Lur'e systems, which is where people like me can start getting interested and so on. And then the C state isn't periodic, but it might be almost periodic, right, or well modeled by almost periodic functions. So the work that I'm going to talk about is motivated by applications in this area, and I highlight a conference paper from last year of mine if you're interested. Okay. Let's have a look. Right, so the purpose of the next set of slides is to give background to each of the areas that will crop up in the main talk. All of what follows is known. It's sort of my take on things, but it will help contextualize the new results. So the first here are passivity theorems. This is a classical approach in control theory. So I show a feedback connection of a plant P and controller C in sort of input-output form. Everything's linear in this case. And the sort of passivity ideas dating back to the work of Ames says that the feedback connection of a stable, strongly passive system, so stable L2 sense, strongly passive, and a passive controller is itself stable and passive. And notice these properties are qualitative in so much as you don't need to know the exact values of C and epsilon, but you might have some physical intuition or other reasoning as to why they exist, right? Okay. So the sort of positivity theorem is a generalization of this result to Lur'e systems, and then we're going to sort of generalize it again to Lur'e inclusions. So speaking of Lur'e systems, what are these? Lur'e is an anglicization of a Soviet name. There are other anglicizations shown in the frame title, and apologies that it's probably not a great approximation of the original name. So these date back to the sort of 1940s or so. They're the feedback connection of a linear control system, here sigma, and a static nonlinear output feedback F, so shown in feedback arrangement. So I'm obviously interested in forced systems, so I have a disturbance or forcing term D. U is my control input, and this is a nonlinear function of the output. There's always a sign convention to make, and different communities make different sign conventions. I'll keep it general for now. So as a Lur'e differential inclusion, this is where does the set valuedness come from? It comes from the nonlinear term. So I replace my little f of y by some capital F, which is now a correspondence or a multi-valued function. It maps subsets of Rm, in this case, to subsets of Rm. So the aim is to construct a passivity theorem, which ensures ISS properties for Lur'e differential inclusions. And then we shall use that to establish incremental ISS for Lur'e differential equations. Okay. So a little bit of background on differential inclusions. So here I have x dot of t not equal to something, but belonging to, in the set sense of, in this case, g of x of t, or a forced version, g of x of t and d of t. So these arise as the appropriate mathematical framework for rigorously describing solutions of differential equations where you have discontinuous right-hand sides or discontinuous functions. So where might discontinuity come from? Well, for example, certain models for friction give you discontinuous right-hand sides. So this is now a classical subject. It's studied in many textbooks. I include some references. And the key object, obviously, are these set-valued or multi-valued maps, also called multis or correspondences. In this case, mapping R subsets of Rn to subsets of Rn. And non-smooth analysis underpins their study. So from a kind of control perspective, there's some nice papers on this subject. I highlight this Automatica paper from 2009. So how about Lur'e differential inclusions? Where might they come from? So I remind you of the equation, x dot minus ax minus d all belongs to f of cx of t. Well, these can arise in a number of settings. For example, to model hysteretic effects or quantized feedback. So I talk about quantized feedback first. That's this diagram on the right here. So quantization, roughly speaking, refers to the process of replacing a continuous signal by a discretized or quantized one. So I have my x-axis with variable labeled y, and this gets mapped to q of y, which is then this sequence of steps. Obviously, this is discontinuous, and this reflects a situation where, for example, my input can only take kind of discrete values. It can't take a continuum of values. And I'll talk about diagram one. This is a sort of diagram arising from two mechanical components moving relative to one another. An example of this is like two gears or something. And the backlash or play phenomena is, of course, where the position of one and its history affects the position of the other, basically. So Lur'e inclusions arise in, for example, these two frameworks. And as I've already said, they also provide a framework for studying incremental stability properties of Lur'e differential inclusions. Differential equations, sorry. Okay. So I'm moving towards the stability theory of such objects. So think a bit again about Lur'e differential equations. I often just call these Lur'e systems. These are hugely well studied, right? This review paper by Leibniz 2006 has like 500 references already. They're still studied, though they still find relevance. For example, nowadays, various neural network architectures like equilibrium networks can be expressed as Lur'e systems. Again, references are sort of shown. So the stability theory of these objects is classically called absolute stability theory. And an absolute stability criterion, as shown on the slide, is a sufficient condition for stability. Now, at this point, stability means many possible things. And it's in terms of the two things that you've got, right? The interplay of the linear system sigma, so that's captured by ABC or its transfer function, and the nonlinear term F. So traditionally, absolute stability comes in one of two flavors. There's kind of the unforced case, G equals 0, and then you're interested in sort of state space properties like asymptotic stability and so on. So this is in your kind of classical control books, the Haddad and Scheller-Boyner or Khalil's nonlinear systems and so on. Or when in the presence of a input term, so D non-zero, you might look at various input-output stability notions, so L2 or L infinity input-output stability. Okay, why the word absolute in absolute stability? Well, the usual perspective is that F is uncertain. It's not known exactly, and it's specified in terms of qualitative properties like normal sector conditions. And ideally, you would like a result which applies to all F in that sector or norm condition. And so somehow the bigger the sector or the weaker the condition, the more systems you include and kind of the better the result. Okay, there are lots of classical absolute stability criteria. I've listed kind of 4 on the slide there. So the real Eisenman conjecture asks if stability of the linear system implies stability of the nonlinear system. Of course, nonlinear stability implies linear stability because you include linear functions in nonlinear ones, but conversely, it's not true in general. But this generated a lot of interest. It turns out that there's a kind of complex version which is true. So despite the name, curiously, it is true. Okay, the circle criterion, Popov criterion, Zabe-Falk multipliers. And essentially all of these impose different assumptions, right? So they treat different Lur'e systems. So a result that we're going to sort of generalize is this sometimes called the positivity theorem. So this is for unforced Lur'e systems at the moment. I've taken a screen grab from this Haddad and Bernstein paper. So sigma is the linear system. If this is strongly positive real, so that's a sort of passivity or dissipativity property. and my nonlinear term, and they call it phi, has this sector condition, then their feedback connection is stable. And it's true for all phi in capital Phi, so that's the kind of absolute nature of the result. So this is going to sort of inspire the results that follow. I speak a bit about ISS. I expect for this audience, all of this is known. This is kind of Chris's take on it. I'll be quite brief. So just consider a controlled differential equation, x dot is g of x and d. So it's called input state stable, or ISS, if there exist comparison functions, psi and phi, such that I can bound trajectories or state trajectories as follows, right? I can get a contribution from earlier states or the initial state, which decays in time, t, and a contribution from the input or forcing term. So I've called here ISS a property of a system. Arguably, it's a property really of a trajectory, and that trajectory could just be 0, 0, the kind of zero trajectory. It can be generalized to sort of zero invariant sets and so on. So script A here. But for simplicity, I'm just assuming that that's zero, basically. And I'm going to call it a system-wide property for brevity as much as anything. So these comparison functions are very kind of useful in nonlinear stability. I'm sure this is known. So K functions are continuous, strictly increasing and 0 at 0, K infinity unbounded ones, and then KL are K in their first variable, fixed second variable, and converge to 0 in their second variable for fixed first variable. Okay, occasionally we're going to mention exponential ISS, and that's a special case of ISS where my comparison functions take a certain form. So I have exponential decay in time, that's the e to the minus lambda s, and then kind of linear growth in the initial state and in the input. And of course, it's worth mentioning that linear systems, if they're stable, are exponentially ISS. But of course, there are nonlinear systems which are ISS but not exponentially ISS. Okay. So as I'm sure is known, ISS dates back to the work of Sontag from the late 1980s, and a flurry of activity followed. So there are now a number of variants of ISS, and it's been extended to many different settings. So I cite the series organizer in recognition of his work in this area, for example. And my own take on it is as follows, that over the past 30 years, it's reshaped substantially how we think about nonlinear stability theory in the mathematical systems and control theory discipline. Right? I mean, it's unified asymptotic and input-output approaches to stability. It's very, very powerful. So I come from a linear systems background originally, infinite dimensional linear systems background, and I note the following, or at least for the finite dimensional case. Stability of the uncontrolled system implies stability of the controlled version, right? So a stability concept for x dot is g of x and 0, uncontrolled, implies something for the controlled version, x dot is g of x and d. For nonlinear systems, this is not true, and it can fail really quite surprisingly. And for nonlinear systems experts, of course, that's not surprising. But when you maybe first meet it, you think, gosh, I wasn't expecting that. So it's possible to just cook up toy examples. I have this g of x and d is minus sat of x e to the minus absolute value of x plus d. Okay, I plot the graph of g here. So taking d as 0, it has the right sign property. So the uncontrolled differential equation has 0 gas, globally asymptotically stable. Solutions converge to 0. But one can cook up an input which itself converges to 0, 2 divided by t plus e, giving rise to an unbounded state. Okay, it grows very slowly, like log of t plus e, but still a very simple example where I get growth even though my input is going to 0. So stability of the uncontrolled system does not guarantee stability of the controlled version. And there are more pathological and extreme kind of examples of this. So I highlight a screen grab from a paper by Thiel and Hesfana, examples of globally exponentially stable systems that can be driven to infinity by arbitrarily small additive decaying exponentials. So I don't suspect that these are very physical, but they're still mathematically kind of quite interesting and surprising. So as I say on the slide here, nonlinear systems need very careful treatment. And as is now known, ISS is a suitable framework for studying stability of a controlled or forced nonlinear control system. Because roughly speaking, small inputs and small initial states give rise to small states. Okay. So I'm interested in ISS for Lur'e systems and then Lur'e inclusions and so on. So a natural question is the following. Right? To what extent may classical absolute stability criteria, which remember are often designed for unforced or uncontrolled systems, to what extent can they be strengthened or enhanced to ensure ISS, right? Bearing in mind that we shouldn't expect them to guarantee ISS alone, because stability of the uncontrolled system doesn't imply stability of the control system in general. So the first work I'm aware of this is by Arkak and Thiel from the early 2000s, where they considered input state stability of Lur'e systems. And they essentially have a version of the positivity theorem, which I showed a bit earlier, and which ensures ISS, I should say. And then there was a lot of follow-up work or sort of complementary work by Hartmut Logemann at the University of Bath and his collaborators and students. And this is sort of where I enter the picture in this story, because we looked at strengthening various absolute stability criteria, like the circle criterion and so on, to try and establish ISS. And the moral is shown, right? Suitably tweaked or strengthened, absolute stability criteria do guarantee ISS. Okay. So that's my sort of background on the various areas. I've now got to the sort of new results for this talk. So we're considering the following forced Lur'e differential inclusion. It's already been shown, but x dot is minus ax minus bv. I've actually picked the negative feedback convention here, so it belongs to minus bf cx of t. So ABC are my linear data as shown. My input is assumed to be locally L1, and f is a correspondence. So we need to impose some regularity on f to be happy that we have solutions and so on. So usually it's assumed to be upper hemi-continuous, values which are non-empty, compact, convex subsets, and 0 at 0. In particular, from quite general theory, these assumptions ensure the existence of maximally defined solutions. So what I mean by that is they're bounded on their interval of existence. And if, I just leave it there. At least for each locally integrable input and initial state x0. So the input to state stability concept for the Lur'e inclusion 1 is the same as before. It's the same as for the differential equation. And I'm interested also in a variant of integral ISS. So I say that 1 is integral ISS with linear gain if I can find comparison functions such that I get the following estimate in the blue box. So I have the same growth in the growth and decay in the initial state. And then I have growth not in the L infinity norm of the input, but the L1 norm of the input. Now, so that's the red term. As highlighted, as different from usual ISS, you might expect a nonlinear gain in there, right? Another alpha or kind of beta function. And I'm basically assuming that that's a constant, and that constant can be absorbed into, it's a linear function, and the constant can be absorbed into phi. Yeah. So our results will ensure this property. So that's essentially why we include it as a definition. Okay. So we're going to focus on a particular class of correspondences. So defined in equation 2, right? So f of y are the w. So if you like, they're the little f of y values, but they're set valued. So we just have w, which are bounded from above by some theta. They satisfy a sector condition. So w inner producted with y has some lower bound in terms of y. And then this is kind of alignment condition, this third condition. And I get to that in just a moment. So this upper bound and alpha, so theta and alpha are both assumed to be continuously differentiable, and alpha is bounded from above by theta. And then these constants have the shown properties. So I referred earlier to this Arkak and Thiel paper from 2002. What's shown on the slide is essentially a set valued generalization of the nonlinear terms they consider. Notice that since theta and alpha appear as bounds, the assumption that they're C1 continuously differentiable is not restrictive, because if they're not, you could replace them by suitable upper or lower bounds, which are C1. So there's nothing, they could be even assumed to be smooth. So this first property is just an upper bound, and this upper bound could be large. It's not going to be limiting. I just need something to get a handle on how big these things grow. And the second property, as I said, is a sector condition. The third property automatically satisfies in the scalar case, right, where m equals 1. Remember, m is the sort of input dimension, if you like. And essentially, it's an orthogonality condition. It sort of says that f of y is not too close to being orthogonal to y, because if f of y or w inner producted with y equals 0, well, of course, this inequality can't hold. So it's a sort of orientation condition. It's possibly the best way I can describe it. Okay. So we have our first theorem. We have our Lur'e inclusion 1 with our class of correspondences f in 2. My pair CA is assumed to be detectable, and there is a positive semi-definite solution to the shown matrix inequality. This is a bit like positive realness, basically. It's a sort of state space positive realness property. Okay, the following statements hold. If my lower bound for my sector belongs to K infinity, so I get a rate of growth for my lower bound sector, then my Lur'e inclusion is ISS. If in fact I have a linear lower bound, so greater than or equal to some epsilon s, then further additional properties hold. Item 2 essentially is semi-global exponential ISS, right? So for each fixed R, which can play the role of a threshold, for initial conditions and inputs which are bounded in norm by R, I can find some constants for which this thing is exponentially ISS. The constants could depend on R. That's the point. Of course, R could be arbitrarily large. It just needs to be fixed. If in fact my upper bound for my correspondence f theta is also linearly bounded, now from above, then I get exponential ISS. Okay, so statement 1 is the sort of more useful or more the one we will be using more later. Statement 2 and 3 sort of flesh things out and fill things out a bit more. Okay, so the first main result. So I suppose it's worth commenting that inequality 3 is a sort of dissipativity assumption or passivity assumption on the linear system, and the sector condition captured by alpha is somehow a dissipativity property on the nonlinear term, and that's why it's a sort of spirit of the positivity theorem. So I mentioned uniformity earlier and the importance that's going to play. So these comparison functions that you get out, what do they depend on? Well, they depend only on the linear data, A, B, C, and these bounding terms which crop up in the definition of the correspondence capital F. Okay, and then the fixed constant R where it appears. They don't depend on anything else, and that's going to be important later. Okay, I'm not going to give the proof in a talk like this, but I just highlight that it's a Lyapunov argument. And what's the Lyapunov function? Essentially, it has two parts. It has a part which comes from the matrix inequality by hypothesis. It has a part which comes from the observer Lyapunov equation, and that's where detectability of the pair AC and the triple ABC is kind of used. And then roughly speaking, both of these terms, the P term and the Q term, so these quadratic Lyapunov functions give you some decay and some growth. And this function H, this nonlinear function, somehow balances out the growth and the decay to give you overall decay. It's probably the best way I can describe it briefly. Notice also that there's this sort of iterative argument. The existence of a Lyapunov function gives you that solutions are bounded on their interval of existence. That then gives you that solutions are global, so they're defined for all time, and then you get the stability property. Yeah. Okay. So I give a second result, which is now a passivity theorem for integral ISS for these Lur'e inclusions. So the hypotheses or the assumptions are very similar. The setup is the same. Lur'e inclusion, correspondence F as in 2, same detectability assumption. I now strengthen my assumption on the solution to the matrix inequality. I now assume that it's positive definite. But I weaken my sector condition. Alpha only has to be itself positive definite, which for nonlinear functions means alpha of z is positive if z is positive. But alpha could decay, right? It doesn't have to increase. It's not at K infinity anymore. Okay, then the conclusion is that the Lur'e inclusion, the conclusion is the Lur'e inclusion is IISS with linear gain. And the comparison functions depend only on the data in the given data. So essentially, this often crops up in absolute stability criteria. You can sort of trade off the assumptions, the hypotheses against one another. You can strengthen some and weaken others and still arrive with a stability conclusion. Kind of interestingly, these hypotheses are sufficient for zero gas of the Lur'e inclusion. So this is a situation where stability conditions for zero gas give you stability conditions or sufficient conditions for stability for integral ISS. Now, the relationship between zero gas and integral ISS is, of course, that integral ISS implies zero gas and conversely no, but the difference is sort of subtle, right? It's quite hard, as I understand, to cook up zero gas systems which are not integral ISS, right? You have to work quite hard. Okay, this proof of the result shown is more subtle because you need some converse Lyapunov function for differential inclusions. So there's a sort of heavier theorem being, in this case from Thiele and Prali, being invoked. Okay, good. So those are the sort of two main results I want to tell you about for Lur'e inclusions. We're now going to see how these translate to Lur'e differential equations, what they tell us for Lur'e differential equations. So a few more definitions. I'm interested in incremental stability. So this is broadly concerned with bounding the difference of two arbitrary trajectories of a given system from an ISS perspective in terms of the initial states and the input terms. So there's a similar theory called contraction analysis or contraction theory, which is trying to achieve the same sorts of aims. And obviously for linear systems, incremental stability is the same as stability by the superposition principle, and obviously not necessarily the case for nonlinear systems. Okay, so the definition is shown just for a differential equation, nonlinear differential equation. Incrementally ISS, if I can find some comparison functions as shown, such that now the difference of trajectories is bounded by difference of initial state or earlier state decaying in time plus difference of inputs. Okay. So we're now going to turn attention to the forced Lur'e differential equation. Sorry, that's a typo. And I need some regularity assumptions on F to make sure that I have solutions of this thing, but I'm not going to state those here. It's a nice enough function, basically. So the key idea is as follows, right? Let's look at two trajectories, vi, xi, so v1, x1, v2, x2 of 5, and let's look at their difference. So define psi as x1 minus x2, and then naturally when you try and form the error system, what term do you get? Well, you get this difference of the nonlinear terms shown here, and essentially I just add and subtract 0. I do this as usual. I can now write this as belonging to a set valued map, a correspondence F. And this will actually be the correspondence F from earlier, provided that F now satisfies some sort of suitable incremental properties. That's the key idea. And then once that's satisfied, once those assumptions are in place, psi, the difference x1 minus x2, will satisfy a Lur'e differential inclusion, and we can use the theory from earlier. That's the idea. Now, it turns out that we actually need to consider semi-global incremental stability properties. So we're going to need to look at initial conditions and inputs which are bounded in norm, at least by some fixed but arbitrarily large by constant. For practical purposes, arguably, though, that's fine. Okay. So the main result then on incremental ISS for these Lur'e differential equations is shown. So I have my forced Lur'e system 5, so the differential equation shown previously, and I'm assuming that F is actually independent of its first variable. In principle, F can depend on time as well as the output, but here it just depends on the output. Okay, I have a detectability assumption, and again, solution positive semi-definite of the shown matrix inequality. So that's my linear passivity assumption. And then these assumptions A1, A2, and A3 essentially imitate the earlier properties of the correspondence capital F, but now they're kind of incremental versions, so difference of arguments for the function little f. So essentially I fix a compact set capital gamma, and then for each such set I can find an upper bound theta of gamma so that f of y plus z minus f of z is bounded by theta of gamma of y. This only needs to hold for all z in the compact set gamma and for all y in Rm. So this is somehow a bound on the growth of f. Okay, the second condition is essentially now a monotonicity condition in the kind of functional analysis sense of little f. It's not quite, because it only needs to hold for z in gamma and, excuse me, classical monotonicity would just be 0 here, and something like it's called strong monotonicity is when alpha is a linear function, so you'd have epsilon y squared, but it's essentially a monotonicity type assumption. Okay, and then I have this sort of orientation condition as before, and this also follows from the previous two in the scalar valued case, right, where f just maps R to R. Okay, so those are my hypotheses. What are my conclusions? Excuse me. So in the positive definite case, P, that's the solution to the matrix inequality, I can find comparison functions such that for all trajectories, that's what B denotes here, the difference between x and z, well, it's bounded by the difference in initial states decaying in time and the integral of the difference of the inputs. So that's a sort of incremental integral input to state stability with linear gain conclusion. And if in fact my lower bound is of my sector alpha gamma is in K infinity, then I get an incremental ISS estimate. And crucially, because I've used the earlier Lur'e inclusion result, the comparison functions are independent of the trajectories, which is crucial for us. Okay, good. So B, just to restate it, B is the collection of trajectories. So pairs, input state pairs. The input is assumed locally integrable, locally L1, gives me a state. And B infinity is where the input is also locally L infinity. So my L infinity norm is fine and makes sense. Okay. So I've just showed the second stability conclusion again. But I comment here that, again, it's a semi-global result because these comparison functions depend on this fixed constant R. But that, for practical purposes, is fine. And as I've said, this follows from the result for Lur'e inclusions by that kind of looking at the difference of solutions argument. Okay. So as a sort of nonlinear, as a nonlinear term that we have in mind are functions of the form v times the absolute value of v to the d. So these are sort of monotone functions, and they're superlinear, right? They grow faster than linearly. And these arise in various viscous damping models. So again, the connection to kind of wave energy. And you can show that such functions do indeed satisfy A1 to A3. Just to comment, why am I making these semi-global results? This is this final bullet point. Well, there is a global version, right? You can take this set gamma. It's been a compact subset so far of Rm. You could take it as Rm. But the corresponding estimate would be that, as shown, you'd need some K infinity function theta, where I get that the difference between f of y plus z and f of z is bounded by theta of y. But that needs to hold for all z and y, and z doesn't appear on the right-hand side. So essentially, you can quite easily show that means that f has to have bounded derivative, right? The functions on the first bullet point don't satisfy that. So this is too restrictive assumption, basically. Okay. So I just highlight that these nonlinear assumptions are a bit tedious to check. You end up doing lots of estimates and so on. I've highlighted a class which, at least a function which does satisfy them. And then for the vector case, so multi-input case, m bigger than 1, diagonal or decoupled functions, so m scalar functions essentially, also satisfy the assumptions A1 to A3 if all the component functions do. And that's quite an important class of examples as well. Okay, good. So I'm now going to move on to then the uses, particularly for entrainment of incremental input to state stability. So I show again the incremental input to state stability estimate. And of course, this is well known, right? The things you can do with incremental stability include sort of synchronization type problems and observer design problems and so on. And here we can use it to establish entrainment. And again, this sort of generalizes this sort of classical linear systems theory, which sort of says that, okay, I have my linear systems, suppose it's stable. If I feed in a sinusoid or a periodic function, well, I'll just stick to a sinusoid for the moment, then not only is my state and output asymptotically sinusoidal, but also the amplitude and the phase shift are determined in terms of the transfer function. So it's a very, very nice theory. And the kind of idea for entrainment by incremental ISS is shown in green. Essentially, you look at not two different solutions, but one solution and a shifted version of that solution, which is also a solution of the same problem, but shifted. Now, of course, if D is periodic, or almost periodic, well, the difference between the two inputs is small. So what that then shows is that, roughly speaking, the sequence of translates becomes a Cauchy sequence in a Banach space. So it converges. And in particular, you can then show that its limit has almost periodic or periodic stability properties. That's the kind of key idea. Okay, so I just mentioned a little bit about almost periodicity. So capital R is either the reals or the non-negative reals. There's no loss. There's no restriction, particularly in working with just the general Banach space. So a set is said to be relatively dense in R, a set S, if you can find L such that these intervals of length L for all A intersected with S is non-empty. So for example, the integers are relatively dense in the reals. Okay, an epsilon period of a continuous function. Tau is an epsilon period of a continuous function if the difference between t and t plus tau is less than epsilon. And we could denote the collection of those as the collection of almost periods, PV epsilon. So a function is called almost periodic if this set is relatively dense in R for every epsilon bigger than 0. Okay, the collection of almost periodic functions is denoted by AP, almost periodic, and that's a closed subspace of bounded uniformly continuous functions on R taking values in X. So to have in the back of your mind, an archetypal example is something like the one shown, sine of 2 pi t plus sine of 2 pi square root t, 2t, t. So this is the sum of two periodic functions. So it's the sum of two almost periodic functions, and almost periodic functions form the vector space. So it is almost periodic, but it's not periodic because root 2 and 1 are not commensurate, right? So there is no period of this. So the Stepanov concept of almost periodicity is similar, but now it's essentially for L1 locally integrable functions, and it's not that the functions take small values, but the difference between functions takes small values, but the difference with integrals of functions takes small values. So we get a set of Stepanov epsilon almost periods called P1 VE. Yes, and then functions called Stepanov almost periodic if for every epsilon this set is relatively dense in R. So notice the key difference is that almost periodic functions are assumed to be continuous by definition. Stepanov almost periodic functions don't need to be continuous. So in the graph, again, probably most instructive, the black lines are a sort of sawtooth wave, that's VP. And then I can just take a sum of those with, again, not commensurate periods. And that gives me the gray lines, which is a quite pretty pattern, and that's a Stepanov almost periodic function, which isn't Bohr almost periodic. There we are. Okay. So I'm coming towards this sort of last set of theoretical results. We're considering these forced Lur'e differential equations 5, and I've now got a fixed Stepanov almost periodic input, so W and S1. So what assumptions do I impose? I want detectability of my pair CA, as before, a symmetric positive definite solution of my matrix inequality. Okay, the nonlinear term F satisfies my earlier assumptions, and I need the existence of a trajectory which has bounded state. Now this follows from the previous points if you assume f of 0 is 0. But for incremental stability, you don't need f of 0 is 0 because you're just looking at the difference of two solutions rather than a solution compared to 0. So the first part, under these assumptions, there is some unique ZAP, so an almost periodic function, so that WZAP is a trajectory, right? So you get the existence of a unique state trajectory corresponding to W. And then you get this sort of shown inclusion of the almost periods. Okay. And then what more can we say? Now let's look at another trajectory, V and X. Excuse me, sorry. If P is positive definite, V is in L1, and the difference between V and W is in L1, then I get convergence of X to my almost periodic trajectory, Z. So what we would say is that X is asymptotically almost periodic AAP. So this is the direct sum of almost periodic functions plus continuous functions which converge to 0 as the argument goes to infinity. And moreover, the almost periodic part of X is ZAP. Okay, if W is periodic with period tau, then ZAP is also tau periodic. So, and then finally, in the case that I get ISS, incremental ISS results, so I strengthen my sector condition, and I assume that my Stepanov almost periodic input is also L infinity, then if the difference between inputs in L infinity at the tail goes to 0, as t goes to infinity, then again I get convergence of X to ZAP. Okay, so essentially what I'm trying to do is provide theoretical underpinnings of like a well-defined frequency response for Lur'e systems subject to almost periodic forcing. And these sorts of results are the foundation of that. Okay, so I speak about a few examples, sort of very simple example, but hopefully instructive. Let's think about a damped mass spring system but where I have a non-Hookean spring. So my spring constant is not linear. My spring is not linear, but is non-linear. Okay, and Z is the displacement. So this may be written as just a Lur'e system, and it's routine to check the solution of the positive, well, the system's positive real, and this P satisfies the matrix inequality. Of course, the nonlinear assumptions depend on the F that you pick, but I've already highlighted this class of examples which do satisfy them. So just as a common sense check, I highlight that the famous celebrated Duffing equation is shown, and this is known to exhibit chaotic behavior for certain Ki values. And obviously, chaotic behavior means that solutions separate, and so you don't get incremental stability. So has something gone wrong here? Well, we can reconcile this to the theory developed presently, is that in the Duffing equation, K2 isn't required to be positive, but for us to satisfy the assumptions of the work, K2 would be positive. So everything's good there. Okay. And then you can form systems of mass spring damper systems, excuse me. So I have a screen grab of a diagram where I just now have two connected masses. So two copies of the previous system. And again, the spring force is nonlinear. So, elementary modeling gives me a Lur'e system again. And now I have a diagonal nonlinear term. So F has components F1 and F2. And of course, if F1 and F2 satisfy the nonlinear assumptions, then F does as well. So I just show a simulation result. So I have the Stepanov almost periodic function I showed you before. So the black line is a sawtooth wave, if you like. The gray lines are an almost periodic function constructed from that. And then the colors match, so the dark lines and the lighter lines, and you see convergence of one line to another over time. So these are the states for one initial condition 0, one initial condition non-zero, and you see convergence. Notice that these systems are subject to the same input. I could also have inputs which converge to one another to something Stepanov always periodic and also see the same behavior. Okay. So that's me just wrapping up now. So I've presented a suite of incremental ISS results for forced Lur'e equations. I got those from a suite of ISS results for Lur'e inclusions. And we're motivated by this sort of positivity theorem or passivity theorem where I'm connecting two dissipative systems. And one can use that to establish entrainment-type properties. And way back at the beginning of the talk, a motivating application is in wave energy control and to overcome the reliance on linear systems, basically. Okay. I want to highlight that I have published some similar work earlier. So I just highlight that there's this paper from 2020, which has a very similar title. And essentially, we have some key technical differences in our assumptions. So in the work shown, we always have functions which are essentially linearly bounded. They belong to finite sectors. So that's captured by the shown sector condition for K1 and K2. This rules out functions which grow superlinearly, like this nonlinear damping term that I showed. So although there's sort of quite a lot of overlap in spirit, there are key technical differences which require different arguments as best as I could see. Okay. Also, just want to take this opportunity to plug an event that I am running. So Andrew mentioned that I organise a UK network in mathematical systems and control theory, and we're having a meeting in July in Edinburgh, and it's free to attend, right? So there's no fee or anything. So we're organising speakers at the moment. Anyone is welcome to attend. So you can find it on Eventbrite. There are also links in these slides. We may have spaces to present. We're kind of populating the schedule now. So if you're interested, just get in touch, basically. Edinburgh is a nice city to visit in summer, so I plug this event. Okay, wonderful. Thank you very much.